Okay, good afternoon, everyone. So I'm Ann Struble, and I am with Systat. And so I am going to talk today about PyDASL. And the concept behind PyDASL is understanding big data through GPU-accelerated graph analytics. And I'll just start out with a quick joke here. I don't know if you guys have heard this one. It's about the analytics developer who's also a parallel programming expert. And it's like, oh, right, actually, those are pretty hard to find. The amount of knowledge you need to either be an analytics developer or a parallel programming expert is pretty deep in both. So to have that much depth and that much breadth is pretty difficult. So we're targeting a need here for simple, smarter algorithms that run efficiently on GPUs without requiring knowledge of the parallel programming or device-specific optimization. So this is kind of the basic concept behind PyDASL is we want to reduce the barrier of use for GPUs on graphs. And by doing so, we're going to enable this simple and smarter algorithms. And so then it can deliver the performance of GPUs through a library of fast linear algebra primitives and built-in analytics. And we have been somewhat successful so far in this. And so an example here is that we have run PageRank on NetFlow data. And the source code complexity of the solution of PageRank is 40 times less complex than other GPU-accelerated graph frameworks, but remains within 15% of the performance. Okay, so graph analytics is what we're targeting here. So why graph analytics? And it's because of the numerous applications of them. So we look mainly at cybersecurity stuff, and there's a lot of applications there, for example, intrusion detection, exfiltration, but there's other areas too in business. There's influence analysis or fraud detection. There's some great applications in biological systems, for example, protein complex prediction, biomolecular pathway prediction, as well as others, and a whole other domains also has some great applications for graph analytics. Okay, so now I'll just kind of give a quick overview of the PyDASL architecture. So if you look on the left there on the bottom, we're built on top of NVIDIA NVGraph. So you do need an NVIDIA GPU chip in order to run PyDASL. And so there's both NVGraph and then the basic NVIDIA libraries. And so that's all C++. And so we've added a Python wrapper around that, and that's what we call that the PyNVGraph wrapper. And so we use that PyNVGraph wrapper and then also some other Python libraries, for example, NumPy, Pandas, SciPy, and SciBox. And then that gives us the PyDASL core runtime, which has various functionality. For example, you can load data into the engine, and that data can be of different formats, including SciBox, CSV, or MTX. There's some data prep API in there that helps put the data onto the GPU. And then we have a custom graph analytics API so that you can write graph analytics. And then in addition to the custom, the ability to add custom analytics, then you can also, there's built-in analytics that we already have in there that you can run. And so then there's a whole integration layer. And so from the programmatic perspective, there's a Spark integration, and that's integrated with PySpark. So you can take, if you already have a Spark ecosystem, then you can easily take the data and run PyDASL analytics on it. If you don't have Spark, then the other possibility is to either use the PyDASL REST API or the command line interface, the CLI. And you can both load the data using those mechanisms, and then you can also run analytics. Okay, so as I mentioned, there's a number of built-in analytics. So I'll just go through those quickly. There's PageRank, which is, of course, is made famous through Google's web search, where that's how they originally ranked the web pages. And so that looks into both the number of edges coming into nodes and then addition the quality of those edges. And then a variation of that is personalized PageRank. And so that looks at in addition to looking at the edges, it also adds a weight to the different vertices in the graph. Then there's breadth first search, or BFS. So that finds all the other nodes that are connected to a given node, and then at what level those nodes are at. There's Newman spectral clustering, which is pretty interesting. It does detection and characterization of the community structure within a graph. And then we have a betweenness centrality analytic. So betweenness centrality, that ranks the nodes based on the centrality of the node, so how central it is to the graph. And and specifically, we did an implementation of Brand's algorithm. And so that in order to determine the centrality, we calculate the number of shortest paths that must pass through a given node in order to connect all the nodes of the graph. So a node that had the most shortest paths between it would have the highest centrality. And then finally, we also have a connected components analytic that just calculates the different subgraphs that belong to the graph. Okay, so now looking into the heart of PyDASL, it's really writing custom analytics. And so there's a few different parts to this. The first thing is there's a few different parts to the API. So the first thing is that it provides a mechanism for exposing these custom analytics to the different interfaces of the REST, CLI, and Spark. And then when you write a custom analytic, the data that's accessible to the analytic comes in a few different representations. There's the graph and the graph transpose, and those are both loaded on the GPU already. And then there's also a CSR matrix representation, and that's just in CPU. Okay, so the main part of the main functionality that's given in the analytic that's provided is this semi-ring sparse matrix vector multiplication. And so the reason that this is pretty powerful is that there's a lot of algorithms that use linear algebra solutions for these graph analytics. And so then you can use this matrix vector multiplication to implement those algorithms. So when you see that function up there, the alpha times A times X and plus beta Y, the important parts is A, so that's the adjacency matrix of the graph, and then X is the multiply vector. And so those are actually, in a lot of the algorithms, those are actually the two important parts, and the other like alpha and beta and even the addition vector often aren't even used. So those are the only required pieces, but the other ones optionally can be provided. Okay, so then the other important thing here is this the semi-ring, and that's actually what operations you're performing. So it doesn't have to be multiply and add. So, and when I say that, it's the adjacency matrix multiplied by the X vector. You can use other operations. So for example, the other semi-rings are a min plus. So instead of doing a multiply operation, you'd be doing a min operation. There's also a max min and an or and. Okay, so that's the main calculation power. But then in addition to that, there are a few other functionality that's provided to the custom analytics. For example, if you're running PageRank, you probably don't want the PageRank of all 5 million nodes in your graph. You probably want the top 10 or something. So there's built-in limit and filtering parameters where you can say, okay, I only want 3 nodes and filter them using this regex. And some other functionality, for example, result formatting. And then additionally, there is other NV graph functionality that's more complex, but it's not as commonly used, at least with the analytics that we've implemented so far. Okay, so now this is the tricky part in terms of getting the display to work. I'm going to show you kind of demo how the engine works, running some analytics, and then writing an analytic quickly, just to show how easy it is, in fact, to write an analytic. So I'm not sure if I'm going to be able to go back and forth between the displays. So this is the simple data set that we're going to use. So just kind of take a picture of that and remember it. And now let me see if I can. So that works for you. Let's see. Do that. Okay, now I can see too. Okay, so the first thing that I'm going to do is start up the PyDASL engine. And it takes one argument, which is it has the defined analytics that are going to be included. Okay, so that's going. Okay, and then over here, we will start up the CLI. Okay, and so the first thing we can do is just do help, and I'm going to make this a little lower. Okay, and now we can see the different commands that we can run within PyDASL. So the first thing we'll do is take a look at the data. Okay, so now we see that we have nothing in there. There's no edges, no vertices. So I'll go ahead and add some data. Okay, so we got that on there, and now when we run data info again, okay, now this isn't a huge data set, but it's not that tiny 8-node one either. So we have 300,000 edges, 313,000 vertices. So now if there's this catalog command, so you can also run help on any of the commands. And so now we get a description. So it lists the available analytics. So if we then just run catalog, now we can see the analytics that are available. Okay, and then if you do help on any analytics, so let's look at PageRank, it gives a description and then usage information. And so there's different parameters that you can put in there, and then it also shows what the output will be. So now we can run PageRank, and we'll put a limit, because we don't care about the PageRank of all the nodes, only the top ones. So we'll just limit it to 3. Okay, so that just ran PageRank on that data set. And so this is a NetFlow data set. So we have IP port pairs, and then it's showing where the traffic is flowing in between. So these are the IP ports that have the most traffic coming into them, basically. So that gives you an idea of how running analytics works through the CLI. And so now we'll take a look at writing an analytic. So what we're going to do is implement BFS, a simple version of it. Okay, so if we look down here at the bottom, on lines 45 through 51, we see a JSON dictionary. And so in order to register an analytic and be able to run it with the PyDASL engine, you need to give it the definition of what the analytic is. Okay, so, and there's just a few things that go into that. The first thing is parameters. So because we're doing BFS, the basic idea is we're going to start with a vertex, and then we're going to find all the nodes created to that vertex. So if you think back to that, actually I can probably pull it up now. So you get to see everything. But to this graph here, so we start with 0, and then we find all these nodes. In this case, all the nodes are connected. Okay, so as an input parameter, the user needs to tell us where they want to start. So we have one input parameter, which is the start vertex index, and that's of type int. And then we just give a description of what this analytic does. That's purely for that help functionality. And then you need to give it a run function. And so we called this run BFS. I'll get back to that. And then finally, we also just say what the outputs are of the analytics. So in this case, it'll be the node and what level the node is found at. Okay, so now we're going back to that run method. And so that has to have a specific signature, which we'll see up here on line 34. And if you think back to earlier, I was talking about how there's different representations of the graphs, and so that just comes in the form of a dictionary. And then you can access any of those within your run method. You can access any of those representations. You get a list of all the vertices in the graph, the number of edges, and then the analytic param. So what the user has actually specified for the input parameters, and those can also have defaults too, so that the user doesn't have to specify them. Okay, so in the case of BFS, we are going to use the transpose. So it gets the graph transpose out of the graphs. And then it gets this, on line 37 there, you'll see it gets the start vertex out of the analytic params. And it just uses that same key that we specify down in the definition. And then finally, there's the actual meat of the analytic. So it's the run BFS core. And that passes in that information that we just grabbed out. Finally, it takes the value of the core and just formats it. So now we can look at what's actually going on here. So in the core functionality of BFS, the first thing we do is we have something called the frontier vector. So the frontier vector is basically the nodes that we're currently working with. So it's whatever nodes we have just found. So we start out with, we haven't found any of the nodes yet. So we just create a vector that's the size of all the vectors in the graph, and we assign it to 0. Except we had that start vertex, so we assign that one to 1. That's the one node we're currently working with. Okay, and now we have our visited vector, which will hold basically the results at what level we found each node in the graph. So if we don't find the node, then we get it -1. So we start out with a full vector of -1s. Except then again, we have our start vertex, and we find that at level 0. So we assign that to 0. And now we've finished with level 0, so we set the level equal to 1. And now we start our computations. And we continue going step by step through the graph until there's no nodes that haven't been visited. So as long as the frontier has any values that aren't 0, then we do another calculation. Okay, and now finally, we're doing the heavy calculation with this semi-ring. So basically, we're multiplying the transpose of the adjacency matrix times the frontier. So in that case, in this first step, it would just be that first node you start with. And so then you find the new neighborhood vector. And so that's all the new nodes that start frontier is attached to. Okay. However, with that new neighborhood, you find all the nodes that you attach to. And so you have to kind of take a look at that, because if you just include and you keep looking at all the new nodes and step out from those new nodes, you can end up in loops because you might have found a node that you had found previously. So you have to make sure that you haven't actually visited any of those nodes, and then if you haven't, then those go into the frontier. If you've already visited them, then the frontier gets assigned to 0 for that node. Okay, and now we can update the visited vector. And so in this case, if we've already visited it, so if it's not equal to -1, and it's in the new neighborhood, so the new neighborhood isn't equal to 0, then we assign the current level. If we've already visited it, so the visited is not equal to -1, sorry, I already said that, then you give it the old visited value, because you want to keep it at the first level you visited at. And then if it is equal to -1, then you update it to the level. Okay, and now we update the level, and then we repeat the process with the new neighborhood. So that's the basic BFS. So notice that we were able to implement this whole analytic in just 50 lines. So then we go back over to the engine, and then we have this register command, and that tells us how to register. So we give it a name, and the name can be anything. And then you give it the path to the module that contains the definition. And then you have to give it that definition of the JSON dictionary. So that's that BFS definition down at the bottom. And I didn't make any typos. So the analytic was registered, and then it shows the description and then the usage. And so now, again, we have that really large data set in there. And so we don't really, I guess I gave it a funny name, but we don't want to run BFS on this really large data set. So now we'll use that little data set. Okay, and now we see we have 10 edges, 8 vertices. And now we can run this new analytic that I misspelled the name of. And we have to give it that start vertex, so we'll just start with 0. Okay, and there are our results. So node 0 is at level 0, because we started there, and then we have node 7 at level 4. So if we go back over and look at our data set, then we have, in fact, we have 0, and then 1, 2, 3, 4 hops out to level 7. If we did the same thing, but started at node 4, then we see those first nodes 0 through 3 are at -1, because we can't reach them because it is a directed graph. And then node 7 is at level 2, which we see there as well. So now we have, you've seen the running of the analytics in PyDASL. We wrote a custom analytic and then registered it and are able to run it. And now if you were to restart with that, it's added that analytic to the analytics file. So if you were to restart, then it would still be in there. Okay, and now, oops. Okay, so now I'm just have here the list of all the CLI commands in PyDASL and the REST API, which we already went through all that, so I won't go through those now. And that's it. So thank you all very much for listening. If you have any questions.
We have time for questions.
Hello, great talk. I'm a little bit familiar with CUDA, and in the stuff that I've used, oftentimes the amount of data you have won't fit inside the GPU's memory all at one time when it's doing the calculation for matrices or whatever. So how does this handle breaking up the data into blocks and all this kind of stuff automatically? Or is that something you have to do before or after? Or how does that happen when the data can't fit into memory at one time?
So you mean on the GPU? Like
Yeah.
onto a single chip? Yeah, so currently it has to fit into a single chip, and that's partly because we're using NVGraph, and that's an improvement that they're planning to make to that. So when and if they do that, then we'd be able to handle that.
Okay. Is this able to use the new unified memory component in terms of?
Yeah, so that's what NVGraph hasn't been using.
Okay.
I don't think they've switched yet. They might have now.
Okay.
Questions? Oops, sorry.
Hi. So given that you need to fit the graph into memory on the chip, how big are the graphs we can currently fit onto, let's say, a good-sized GPU?
I don't know the answer to that.
Okay.
Yeah.
Biggest graph you fit onto a GPU
The
recently?
biggest one I've done is 20 million edges, but I think you could go into the billions. I don't know. I haven't tested it.
Okay, we have time for 1 or 2 more quick questions, assuming that the lightning talks won't start late. Any questions? All right. Oh, no, there we go.
I was wondering how you measured code complexity to assess the 40 times reduction.
It's all in just source lines of code, not, in terms of.
Okay, can we please thank the speaker again and thank all